Hi, I'm Mike Schnecker, Business Development Manager at Rohde & Schwarz. And today we're going to show some measurements of signal integrity on the RTP164 oscilloscope. The RTP164 is a 16 gigahertz bandwidth oscilloscope with 40 gigasamples per second at that bandwidth, and a large set of tools for both signal and power integrity measurements. Now in this demonstration we're going to show how power integrity directly affects signal integrity. So I've got a setup here with a USB memory stick. It's a pretty common memory drive that most folks use on their PCs. This is USB 3.0 technology, so it's running at 5 gigabits per second. Got it plugged into a fixture and I'm monitoring the signal lines differentially on the scope. And so we're looking at an eye pattern of the signal. Eye patterns are a great way of looking at signal integrity. A couple of things that people like to do is observe the noise and timing jitter on the signal. And a lot of times they'll put a mask in the middle that indicates an area where you really don't want the signal to go. The interesting thing about the mask testing in the RTP is we can do this as a live eye. So we're doing it actually in real time. So I can actually disturb the signal path and you can see in real time the effect of my just touching on the wires here. This is something that no other scope can do. It's very helpful for debugging applications. Now this is a pretty decent looking eye. It looks pretty clean and open. You see a little bit of separation there. That's something that's called pre-emphasis. It's designed to allow for the signal to travel down a longer wire without distortion. We're going to show another thumb drive, just a different one. Nothing modified here. This is actually another off-the-shelf device. And you can see the variation. So this is the eye pattern of device number 2, we'll say. You can see it's actually failing on the mask on the sides. There's a lot more noise or jitter in the timing. And in fact, it looks like a little bit more overshoot in the signal amplitude as well. So having seen this, we clearly know that one is better than the other. We'd like to maybe analyze a little bit better the sources of these problems. So one of the tools that we have is something called our advanced jitter application. And advanced jitter allows one to dig into the details of the measurement results. So I'm going to select a new setup here. Actually go over here, and we're going to open this setup file. Here we have an analysis of drive number 2. This is the one that really had the rather ugly looking eye pattern. As you can see, this eye pattern we call synthetic eye on the top right shows the characteristics that we were noticing when we looked at the live eye, that overshoot. There's a couple of interesting displays that we can do in our software that are unique. We're able to derive a step response from the channel. So this step response gives you a clue as to why the signal looks the way it does. If you look, you can see that when the signal rises, it overshoots a lot and then rings a lot. This part of that step response is why you see the eye overshooting like that. That's part of the problem. So we definitely have some sort of a signal integrity issue in the actual launch from the chip. Then there's also over here the jitter parameter. So jitter is made up of a number of different components, including random jitter and data dependent jitter, which is caused by the channel. But there's also something called periodic jitter, and a lot of that comes from power supply switching. So we're seeing here 16 picoseconds of periodic jitter on this particular drive. We're going to focus in on that measurement. So I'm going to redo the measurement now on drive number 1, the one that had the nice clean eye pattern. So we'll plug that guy in. And then I just reacquire a signal and recompute the jitter parameters now for the better looking eye pattern drive number 1. So this will take probably about 30 seconds or so to compute. Here are the results for drive number 2, and you can see there again, there's that clean eye pattern that we had noted in the live eye display. You can see on the step response, it's much cleaner. There is still an overshoot, but that again is the pre-emphasis that is intended. But you see how it settles out much more quickly and much more level. So that's why this eye looks better than the other one. Looking back at the periodic jitter that we noted on the other drive, you can see now the periodic jitter is only about 8 picoseconds. So we have but roughly half of the periodic jitter on this one. And again, I mentioned that is coming from the power supply. We can look at the components of the periodic jitter on this table. This actually shows you the frequencies and amplitudes of the periodic jitter. And there's a lot of them around 300 megahertz. And then there's one component here at around 2.5 megahertz. These are the ones that will be caused by the power supply switching. If you look down the table a little bit farther, you'll see there's some high frequency ones. These are all vertical ones that are actually caused by the amplitude of the signal varying. So again, we see rather large amounts of periodic jitter in the lower frequency range. A lot of that's coming from the switching power supply. So step 3 might be, okay, what is it in the power delivery that might be causing this problem? So one of the issues with power supply noise is the impedance of the power distribution network, or PDN. On each one of these chips, it has its own power distribution network, and it's really just usually a capacitor, maybe to filter out the noise. We can analyze the power distribution network impedance using this instrument and a couple of extra accessories that we have here. So I'm going to configure this to measure that impedance now. So we're going to essentially unpower the device, and we're going to connect to these accessories a pair of coaxial cables that have been soldered right across the power rail. So there's actually two coaxial cables that are soldered together across that power rail. And we have a feature in the oscilloscope where we can actually measure this power distribution network. So I'm going to preset the oscilloscope to get back to its default state, and then we're going to run this software that is able to measure the impedance. And the way it does this is that scope acts as a network analyzer. We have a source generated by an internal generator, and we're going to generate a test signal, measure that test signal relative to the signal coming through the power distribution network. So let's launch that software, and I'm just going to go down to the desktop of the oscilloscope now. Here's the software interface, and we're going to recall a saved setup as well, so we can set this up more quickly. We want to start, in this case, we're going to start the sweep at 10,000 hertz, and we're going to go out to 100 megahertz, so that's the frequency range. And we just want to make sure we set up the input and output channels correctly. So it's measuring on channel, or reference on channel 1, measurement on channel 3. And then we'll just run off a test here. And it's going to trace, sweep the frequency from the 10 kilohertz on the low end. And so now we're sort of tracing out the impedance. The vertical dimension here is milliohms. So right now the impedance is running just about 2 ohms at 10 kilohertz. And this is typically what you'll see. The impedance drops versus frequency. That's characteristic of a capacitor. Capacitors have increasing impedance with frequency. At some point it's going to hit a resonance or a low level, and then it's going to turn around and start increasing. The increasing part is the inductance of the power rails and the capacitor itself. So you actually have a resonance, and this is pretty kind of common as well. What we're interested in is how low the impedance gets. The lower the impedance of the power distribution network, the less noise can get through to the device under test, the less power distribution network noise. So we saw in the periodic jitter measurement that there was some extra noise coming in at this frequency range. We're running this test to see if indeed the power rail is part of the problem, power distribution network. So again, we're sweeping this out. Okay, so you can see we swept the measurement from both devices. Again, this is impedance on the vertical axis and frequency on the horizontal axis. The red trace is the thumb drive with the higher noise that we noted. And you can see that the impedance of this drive is more flat and is actually higher. It's actually about 1 ohm minimum. And it doesn't have very much resonance to it. It doesn't really have a peak there. But whereas the good drive, the blue trace, has a much lower impedance. It actually goes down near 1/10 of an ohm at the lowest point. So it's much lower impedance. It allows less noise to get in. And you'll notice in the frequency range here, this is 100 kilohertz here, and this is 10 megahertz here. And we noted that we had that frequency component right around a few megahertz, 2 megahertz, and also around 300 kilohertz. That is where the noise is getting in. So we've actually been able to correlate the problem with the power distribution network and the result that we had on the jitter, and even bring it down to the specific component that's causing the problem, in this case the capacitor. I think a better capacitor would provide more noise rejection in this case. Not to say the drive's not working, but it could be better with the right power distribution network. So to learn more about the RTP164 and any of these measurements, please visit our website at www.roda-schwartz.com. And thanks for joining us.